Okay, I've got a curious circuit here. It's called an averaging integrator, and normally I don't do videos on this unless I get some kind of surprising result or there's a good learning opportunity on the circuits that I built. But this is certainly one of those. Basically, I used a 741 dual 741 op amp of 1458, but it's actually a Hitachi 17458. But I believe it's still supposed to be an equivalent. That's how I have it. Um, these are like equivalent circuits. It actually is supposed to act like a capacitor multiplier, more or less. But it's supposed to basically take a signal input and then average the output, right? To give you an average level. And, so if you got a DC signal, it'll give you an average of the DC as an output. If it's an AC signal, it'll give you like nothing because it's average. Now here's the circuit there, and here's the circuit board. I'm not going to show you the schematic because it's shit. But basically, it's the same as in the book. It's just the op amp is a 1458. Otherwise, it's pretty much identical. Um, there's the actual circuit. So, um, and I've got, basically that's the output, and that's the power. I mean, that's the input signal right there. The power is the orange wire there, and I've got it at plus or minus 12 volt. Now, um, what's interesting about this, and here's the signal I got, right? Um, and I've got a 1 volt offset applied to it. Alright, and you can see the yellow line is the output of it, and the blue is the signal I'm applying to the input. Now, if I take our output down to 0 volts, watch what happens. Okay, it's floored, right? That's what you kind of expect. It's showing the average. You do it 5 millivolts. Don't see much at this scale because that's the settings I got. Half a volt per division, etc., and half a volt on the input as well. So I can take it to like 20 millivolts. You're starting to see a little bump in it. Um, at 100 millivolts, you're definitely seeing a bump in it, and it's hard to show you what the voltage is. Notice the maximum, two maximums. Channel 1, is the yellow trace. Alright, that's 178 millivolts, and that's our output, and 1.2 volts is our input, which corresponds to, our amplitude. Um, but like I said, channel 2, ignore that. It's the 2.3 volts that's our actual input signal, but you're not really seeing what the offset is. The offset's 100 millivolts. It's 100 millivolts this thing's looking at because that's going to be the average since this is an AC waveform. But every time I add an offset, like I'll take it up to 200 millivolts, see the whole thing shifts. It's shifting the sine wave up and up and up, right? And you can put a square wave in it, get the same thing, a triangle wave in it, right? Get the same thing. Let's go back to the square wave. Let me change the symmetry, to like 75%. Whoop, jumps up because the average is increased. Let's go down to 10%, way down. All right, 20%, etc. So, that's what they test in the book there that you saw is, a square wave. But, at any rate, keeping it to the sine wave, um, I got it at half a volt. I'll set it up to a volt. So you can see, and again, you've got a potentiometer on that thing so I can actually adjust the scale factor. I got it about 1.5 to 1, but since I used a one of those, you know, cheesy single turn potentiometers out of my fire damaged junk box. I've had that thing probably for 30 years. Um, that's about the best I can do. It's just too sensitive to make proper adjustments because I'd like it to get it like a 10 to 1 or something like that. But at any rate, it is what it is right now. I'll just leave it at that. But what's interesting about this is not just the fact that it's an averager, okay, which is kind of cool in and of itself, but given the fact it's a 1458 op amp with a 1 megahertz frequency range, I'm really shocked at what this can do. Let me adjust the um, scale here, and let me start scaling up the frequency. Now notice the frequency setting. We're at 3 megahertz right now. Let's see. No, we're at, that's wrong. Yeah, this thing can't get a good reading on it. Hold on. Let's see. Yeah, we're at 1.4 kilohertz. 3 megahertz, my ass. Yeah, this can't get a good reading. Let's see. But now we're up to 500, 800 kilohertz. Okay, and we're still working. Notice the yellow line, its position in general, 1.5 volts. So, now we're up to, we really are up to like 2 megahertz right now. So, and now we're at 3 megahertz. Yellow line's still basically in the same average place. So it's still picking up. This thing is still working. Now I'm up to 22 megahertz. Okay, so much this thing can't even get a proper read on it because of our scale here. Let's see, that's like outside the limit of the scope. This thing is working clear up to the limit. I mean, you can see what the level is. It has not changed, and we're at like, we really are at like 22 megahertz right now. For a 1458 op amp with a unique gain bandwidth product, of 1 megahertz, it just blows me away. I thought this thing, anything like this would crap out at 1 megahertz. Now let me see if it's actually still working. Okay, because again, it's still looking at this as an AC wave, right? And so let's go down to half a volt instead of 1 volt that I had it set at. Oh, guess what? This thing's still working. I mean, it's actually still working. At 22 megahertz, say I'm changing this offset, 100 millivolts, etc. This thing's still working. It's still detecting the fact that that's a sine wave, and it's looking at that offset. So, I'm just surprised this thing's responding. I mean, it's mostly looking at the DC level, but remember, I'm not actually applying a DC voltage per se. I mean, it's just I'm shifting a sine wave. Let me go down to a lower frequency here. I'm just shifting a sine wave. There's no actually DC voltage in here per se. I mean, there is a component obviously because it's being shifted, but I guess this is reading that that component still at very high frequencies. It's just remarkable. This thing still responds like it does as an averager. Right now I got it set at 3.6 megahertz or so. I just switched waveforms. Let me up it to half a volt. Alright, yeah, steady as a rock. Let me change the symmetry now, back to 30%. Okay. 40%. 65%. I mean, basically, yeah, it's still working as a, it's still doing its job. So, go down to 80 up to 80%. Down to back down to 50%. Let's see, 30%. 15%. Oh, I'm changing it. Well, changing the symmetry. Let's go back to square wave. See, square wave is actually going negative now if at 15%, because it's still an AC square wave we're generating here. So, and it will read both directions too. This demonstrates that. It's bidirectional. Right now I got it at 30%, and that's at the, you know, 0 point. That's above 0. That's below 0. I got it at 20% symmetry. 25% is closer to 0. So yeah, at 3 megahertz, this thing's certainly still working. Even that barely looks like a square wave, but it probably looks better than that. Remember the noise on my system. But go back to a sine wave, and we're back to that. So, but at a square wave, let's leave it at that. Let me go to like 60% symmetry. So that puts it there. Now let's up the frequency. Okay, well, this thing's so capricious. But yeah, it's even 13 megahertz are fine. Hey, how capricious this is. But yeah, the sine wave, the output is still generally in the same place, and we're back up to 22 megahertz. So, that's 13 megahertz, 5 megahertz. So if you want a good averaging integrator, man, this thing will work to outrageous frequencies. I just wouldn't expect an op amp circuit, you know, with basically poor specifications. Remember, this is just a dual 741. I'm shocked that it works not just even anywhere near 1 megahertz, let alone 25 times that. So that just blows me away. I thought op amp like this would have shut down well before its gain bandwidth product. Especially this being an application of it. But yeah, this is, like I said, it's just kind of a very unexpected results to see any, because even my best op amps I wouldn't expect to do this, the ones I have on hand. So it's shocking. It's averaging it, but it's amazing that it functions like it does at such a high frequency, given the fact it's an op amp circuit, and we're basically throwing a sine wave. I guess it's just really good at filtering out that DC component. So, and it's good at keeping that even at high frequencies, which is just unexpected. Again, it's probably people that are more seasoned at these things than I am, are probably looking at it and say, well, of course it does, but it's not supposed to operate at frequencies like that. Yet it is. It's actually producing useful results with high frequency involved in it. That's what's surprising. So, anyway, I just thought that was interesting, so I thought I would share it because it was certainly unexpected.